It's a new day, and you know, cause my shirt is different. Hi, we're back. It's still July for me, but it's the future for you. And we're going to talk about classification of matter. You should be looking at this flow chart. It's a big old flow chart. There's a lot to fill in. I'm going to zoom in a little bit so that we can go ahead and see what I'm writing a little more easily. So, classification of matter. Basically, whoops. Spoilers. Okay. Go back. There we go. Let's try that again. Classification of matter. Everything in the universe is going to be described here right now by me, but in like extremely general terms. Much of science involves describing the universe, and to do this, we have to classify the things that we encounter. Everything in the universe is made up of either energy or matter. Is one or the other. Like, it's got to be one or the other. Energy is the capacity to do work. You can see energy like light. You can feel energy like heat. You cannot touch it. You cannot smell it. Energy is what we're going to talk about in Unit 13. Meanwhile, Units 1 through 12 are all about matter. You'll talk about energy a lot more when you take physics. But most of chemistry is going to be, well, you can see 12 of the 13 units are going to be about matter. Matter, hopefully you know this already from middle school, matter is anything that has mass and volume, right? In like middle school or elementary school, you might have said has mass and takes up space. But like we're working on becoming grown-up scientists here, so instead of takes up space, we're going to use a vocabulary word, volume. That's what volume means. It takes up space. Anything that has mass and volume is matter. You can feel it, taste it, smell it. Your body knows how to interpret matter. Matter can come in two types. It can be a pure substance, which means that there's only one kind of matter. A pure substance must be separated chemically, meaning like you're going to have to break some bonds if you're going to separate those pieces. And you could also have a mixture. A mixture would be formed when two or more substances are physically combined, like you mix them. A mixture would be you're just mixing stuff, stir it together. All substances in a mixture retain their properties, and those can be separated physically. They can be picked apart. Now, sometimes separating them physically would be time consuming and no sane person would do it. But like technically you can pick it apart. That's what makes it a mixture. We'll talk about that more some as we look at the bottom half of this chart, huh? So since I have cut my picture up, no, why? Mild technical difficulty. There we go. Okay. So since I've cut my chart up, I'll just go ahead and remind you, this is your pure substance side, and this is your mixture side, which it's sort of implied that that would be impure matter, right? Okay, so for your pure substances, there are two types. You can talk about elements and you can talk about compounds. Either way, there is one type of matter there. Basically, like if you look at this picture, every piece is identical to every other piece in an element. And that's also true in a compound. Your pieces just have multiple things stuck together, but then every single one of those pieces would still be identical to the others when you have a compound. Elements are found on the periodic table, and they are made up of only one type of atom. A compound is when you have two or more elements held together by chemical bonds. So they're stuck together by chemical bonds. That's why they can only be separated chemically. A compound has what's called a fixed composition, meaning like there's a ratio always involved. Like this could be a water molecule right here, where there's always 2 H's for every 1 O. Always, like every water is 2 H's and 1 O. That's a fixed composition. The ratio is the same every time. And a compound cannot be separated by physical means. Like, again, if we're thinking about the compound water, I mean, yes, I could pour some water from my cup into a sink and technically I'm like separating it, but that's not what it's talking about. It's talking about if you wanted to take the different types of matter apart, if I wanted to split up these H's from the O, I would only be able to do that with a chemical reaction. I can't just take the H's off of the O and separate those by hand. I need to react something if I'm going to do that. That's what a chemical separation would be. Mixtures. We have 2 types, heterogeneous and homogeneous. Think back to biology. You may remember the word homozygous and heterozygous. These prefixes hetero and homo have the same meanings here that they did in biology, where heterogeneous means different. Genius, we'll get to that in a second. The homo part means the same, just like heterozygous and homozygous when you were doing genetics and biology, right? The like homozygous was when a gene was like both the alleles are the same, and heterozygous was when a gene was like 2 different alleles. You remember that? Remember biology? You don't remember biology. It's fine. That's my job. Actually, that is your job, but I didn't want to embarrass you. Okay. Heterogeneous and homogeneous, different and same. Basically, again, that prefix hetero means different because each sample taken will be different from the others. Heterogeneous mixtures look different throughout. You can like literally see the differences like with your eyes. They are poorly mixed. So like a salad, if I take like this bite right here, I'm gonna get something different than if I take this bite over here, right? I can look at the salad and be like, I see parts that look different to my eyes. That tells you it's a heterogeneous mixture. It's not mixed together very well because I can easily get different parts out either visually or literally like with my hands. Same with like pulpy orange juice. I don't know if you can read it, but it says pulp right there. You can look at the pulpy orange juice and you can see like, okay, here's the kind of watery part and there's those little solid pulpy parts that like most teenagers seem to hate. I love pulpy orange juice personally, but maybe that's just an old person thing. But yeah, this is lots of pulp. When you're looking through the bottle, you can see there's the pulp, there's the watery, juicy part. I can see the differences and it is poorly mixed. Homogeneous, the homo again means same. Each sample taken will be the same as the others. It looks the same throughout. Like with your naked eye, you cannot see differences. Yes, if you got it under a microscope, you'd be able to. But with your naked eye, you're not going to be able to see anything that looks different from anything else. Like this Gatorade, right? Gatorade's a mixture, right? You know, there's water in there. There's also electrolytes in there. There's also food coloring in there. That's a mixture. It's not just the element water. It's not just the electrolytes. It's like all this different stuff mixed together. So that's a mixture. But if you take a drink from the top of the bottle, or if you stick a straw in and drink from the bottom, you're still going to get the same stuff in each sip. Like you're not going to, it's not like the pulpy orange juice where if you stuck a straw in, you would get a mouthful of pulp if you didn't shake the juice up first, right? With the Gatorade, it doesn't matter if you drink from the top or from the bottom. You're going to end up having the same mouthful, identical mouthfuls to each other. And also when you look at it, you can't see the difference, like the top and the bottom and the left and the right, they all, the middle, the outside, they all look the same. That's a well-mixed mixture. And then alloys are a special type of homogeneous mixture of two metals. So like if you've heard of brass or steel, brass is a mixture of copper and zinc. Steel is a mixture of iron and carbon. When you look at a sample of brass or you look at a sample of steel, all of it looks the same. Again, to your naked eye, if you were able to get a zoomed in far enough microscope, you would be able to see like, oh, here's some steel on a little keychain, okay? And you would, if you were close enough with a microscope, you'd be able to be like, oh, there's some iron atoms and there's some carbon atoms. But like to your human eyes, it just all looks like the exact same stuff being made out of it the whole way through. That's a well-mixed, homogeneous alloy mixture. The word alloy is going to be a key word for homogeneous mixture. If I ever say that you need to classify like this alloy, the word alloy should like ding, 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 immediately an alarm bell goes off in your head and you go, oh yeah. That is a homogeneous mixture, all alloys, yeah. Just like that. Okay, here on the next page, we've got a little flow chart for you similar to the previous one, but it helps you kind of walk through it by asking you questions to identify what type of matter it is. So like I will at some point very soon give you some examples and ask you to identify ultimately, is the thing an element, a compound, heterogeneous mixture, or homogeneous mixture? I'm going to ask you that for all kinds of stuff. And this flow chart on this page is going to help you answer those questions. So like, let's say that the example I give you is a gold bar. First, you would ask yourself, can it be separated physically? Meaning when it's pulled apart, each piece is made of identical matter, or when it's pulled apart, some pieces are made of different matter. If I like hammered a gold bar until it like broke into pieces, would each piece look exactly the same? And the answer is like it would all look the same. So can it be separated physically? No. That means it's a pure substance and I have to decide, is it an element or compound? So I ask, is there more than one type of element? If the chemical formula has one capital letter, then there's only one type of element and it's an element. If there's two or more capital letters in that chemical formula, that tells you it's a compound. Gold is AU. You know that just from looking at a periodic table. Here's gold right here, number 79. Gold has one capital letter, it's AU, that tells you, oh yeah, this is an element. Okay, similarly, here's a glass of water. If we were thinking about water, can it be separated physically? To answer that question again, like if I were pulling apart water, would each piece of water be the same as all the other pieces of water? The answer is yes, they would be the same. So is it being separated physically? No, you cannot separate it physically. Then is there more than one type of element? The chemical formula having only one capital letter would make it an element. If there's two or more, it would make it a compound. Well, I see an H and an O, that's two capitals, that makes water a compound. Erase. Okay, let's look at pulpy orange juice. Can it be separated physically? Meaning, if I pulled it apart, would some pieces be different than others? Yeah, if I pulled it apart, I would have some like water pieces and some pulpy pieces and some juicy pieces and some flavor pieces. Yeah, it would be able to be separated physically. So then you ask yourself, is it uniform throughout? Meaning, are there differences visible to the naked eye, or do all the portions appear identical? If I look at orange juice, pulpy orange juice, does it all look the same? Yeah, it all looks, or excuse me, no, it does not all look the same. You got the pulp bits, you got the watery bits. No, there are differences visible to the naked eye. That's what tells me that pulpy orange juice is heterogeneous. And you could do the same series of questions for Gatorade. Basically, when it's pulled apart, some pieces are made of different matter than others. There's water in there, there's electrolytes in there, there's flavoring in there, there's food coloring in there, there's sugar, so much sugar. So yeah, there are pieces that are made of different matter than others. That tells me it's a mixture. And then to decide what kind, all portions appear identical to my naked eye. So that tells me that Gatorade's homogeneous. Erase. Okay, let's continue forward by looking at the next page. Gotta change what window I'm presenting from. There we go. Okay. Here are some practice problems for us to do together. We're going to do some examples of elements, compounds, mixtures, blah, 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 and then we're going to classify some together. Examples of elements. To find examples of elements, you literally just need to look at a periodic table. Just pick them off the periodic table. I'm going to give you some of my favorite elements. I really like Mn, that's called manganese. I really like antimony, Sb. The reason I like it is because it's got such a ludicrous symbol. No other reason than that. And personally, I'm also a big fan of potassium. There you go. Those are some element examples. Compounds. It says water right here in the picture, but can you think of any others? Maybe one from biology. You know this guy? Does this look familiar? That's glucose, my friend. Okay, and then there's one that is probably sitting on your kitchen table in a little shaker. It's like a white, grainy substance. Salt is sodium chloride. NaCl, that's salt. That's a compound. And then there's quite a few in the air to choose from. The big one that's causing some climate change problems would be CO2, carbon dioxide. You're probably familiar with that. That's a compound. Notice, again, if we're looking at the difference between elements and compounds, notice that every piece of the element looks the same. Some of these are shaded differently because they're supposed to be like in the background farther away. But every piece of the element looks the same. It's a pure substance. Every piece of the compound is made out of the same stuff. The compound is a pure substance. But what's different about the element and the compound is how many elements there are. An element, there's literally only one element and one capital letter. For a compound, there's more than one element, more than one capital letter. That's your difference between elements and compounds. Heterogeneous examples. For your kind of mixture, the example they gave us right here is wet sand. Another really common, easy to think about example would be like fruit salad, right? It's just a bunch of different chopped fruits. It's really obvious to like see different ones next to each other. It's like not a lot to figure out. Right? It's like, oh yeah, that's a strawberry, that's a cherry, that's a piece of apple. Okay, it's different stuff. I get it. It's poorly mixed. Or like cereal. Most cereals are all kinds of stuff like Lucky Charms, right? You got all kinds of stuff going on there. Or Alphabets with marshmallows. Do people still eat Alphabets? Fruity Pebbles, okay? Very obvious differences when you look at it. That tells you it's a heterogeneous mixture. How about a non-food example? What about just like a pen? What about a pen, right? You got like the outside plasticky part. Sometimes pens are clicky and sometimes they have a cap, but that's like a different kind of plastic. Then there's the inside plastic where the ink is, and also the ballpoint tip, and also the ink. Like these are all kinds of different stuff, and you can see the different stuff when you look at it, which tells you it's a heterogeneous mixture. We've also got some homogeneous mixture examples. Tea with sugar. If you dissolve the sugar in there, the tea all looks the same. You can't see differences with your eyes, but it is a mixture. There's tea, there's water, there's sugar, there's all kinds of different stuff in there. But you can mix it well and it will all appear to be the same. Similarly, like coffee, just coffee by itself actually is a homogeneous mixture. Once you've filtered it, right? Like, because there's water in there, but there's also caffeine, and there's also like all the coffee, delicious coffee flavor. And when you look at it, it all looks the same. Another example would be like Kool-Aid. When you're done mixing it, it's all just, you know, purple drink. It all looks the same. It's well mixed, but there's different stuff in there. And then like, again, let's do a non-food example. What about like laundry detergent, right? Like you pour it out of the bottle. I guess I should specify liquid laundry detergent, but you pour it out of the bottle and it doesn't matter if you're getting like the first cap full or the last cap full. It's all going to do an equally good job of cleaning your clothes. So let's do some identification together. Pizza. Is pizza an element, a compound, heterogeneous, or homogeneous? Well, pizza's not on the periodic table. Pizza's definitely, honestly, should be kind of obviously a mixture, right? Because I know there's like bread and there's cheese and there's like whatever toppings you put on there. So that's definitely going to be one of your mixtures. And you have to think about, does it look different when I look at it or does it look the same when I look at it? And I can see differences. I can see the bread. I can see the sauce. I can see the cheese. That tells me pizza is a heterogeneous mixture. Another one on here. Let's go to number 4, water, H2O. They actually give you a formula here. They're trying to give you a shortcut, so you don't have to like spend too much brain energy trying to figure it out. There's 2 capital letters in a formula. That should tell you that that's a compound. If there's more than 1 capital letter, that should tell you it's a compound. And that should be all you have to look at. Another example, we can look at number 6 down here, iron. Again, they're giving you a formula with only 1 capital letter. That should tell you it's an element. And then the last one I want to look at number 9. This one's a little tricky because there are 2 things here. So that's 2 capital letters, but you'll notice these are not connected to each other. Like water, the H2O was like 1 chunk, but this is saying like you have a chunk that's copper and you have a chunk that's zinc. So this is actually an alloy, which makes it a homogeneous mixture, and you got to look out for those. Okay, then we got some pictures down here. These are tanks of labeled oxygen gas. So we have to decide, is it an element, a compound, homogeneous, or heterogeneous? And when we look at it, there's only 1 capital letter in that formula that tells me this is an element. And you can just put an E for element, that's fine. This is a cup of coffee. And when I look at it, it all looks the same to me. What do I know about coffee? Well, it's a mixture. You have to have water, you have to have coffee, and like caffeine. So it is a mixture, but if it all looks the same, that tells me it's a homogeneous mixture. Over here, we got some mixed nuts. It's not an element, it's not a compound, and I should know that immediately because when I look at it, I can already see differences. There's like 4 or 5 different kinds of nuts in here. So it's definitely got to be a mixture. And again, if I look at it and see differences, well, that's going to be a heterogeneous mixture, my friends. And then this last one, this is a picture of salt. I don't know if that's obvious from the picture or not, but this is salt. And salt is, as we talked about at the top, sodium chloride, NaCl. That is 2 capital letters in a formula, so that's a compound. Yeah, the next page has some practice problems for you to try on your own. See, it says independent practice. So, hop to it. Good luck.